Okay, so good morning, everyone. So this is a lab for this week. And if you look at the question, you will see that this is the actual questions for assignment 1. Well, you see, that's why assignment 1, the marks is only 1.5%. Okay, so it's just a way for you to study the lab questions. So now, if you look at the question, okay, question number 1, say that you define a Hilbert matrix. Okay, and the Hilbert matrix has the formula like this. The entries Hij just given by this formula, 1 over I plus j minus 1. But you don't have to implement this because, MATLAB has a function, like if you give any input n, then it gives a Hilbert matrix of the size n by n already. And now what you need to do is write a script, okay, that print out the condition number, of the Hilbert matrix. And you stop the table once the condition number is larger than 1 over epsilon. Okay, so you should get some table like this. So who has done this in MATLAB Reader? So please, share your code, in the chat box. Anyone? Have you done this? No one? Or well, at least some of you have done this. I saw many people have done it on MATLAB Reader. Anyone? So you haven't tried it. Anyone have tried this one? No? Okay, so well, then what is the first step? Okay, so now maybe I have to do it like step by step. Yeah, so I share my MATLAB. So the first step is you just create a new script. Okay, and the script will have the name Hilbert not M. Okay, so now what is the first step? So how do you print out the table? How many printf? Yes, but printf is one line, yeah. And how do you print out the whole, the whole table? So maybe printf just give you the very first, the very first line of the table, or maybe the first 3 lines of the table like this. Okay. And then printf yeah, and in the middle you have n and condition number. Okay, and now what is the next step? So this one is just print out the first 3 lines of the table. So now how do you print out line by line? So how do I print out line by line? Anyone? So anyone have done this? No one? Well, at least now is a good time to do it. So, I mean, what is the next command? How do you print out line by line of the table? Well, so I have a while loop. Yes, you can use a while loop. Yes. So what is the condition for the while loop? Okay, so there's some condition like this, and you have n, while loop. So then that is what is the condition, and then what is inside the loop. So we do it step by step. Yeah. So what is the condition for the while loop? And kappa less than epsilon. Yes. But then what is kappa? Now, when it hit line number 5, it will say that kappa hasn't defined. So then what is kappa? Suppose you run it, it will say that kappa does not define. You can try it. So you have to define kappa. So what is kappa? Let kappa equal 0 first. Yeah, so good suggestion. Yes, so kappa equals 0. We can say kappa equals 0. That is okay. Yeah. And if kappa equals 0, then kappa less than 1 over epsilon. So 1 over epsilon is a big number. And what is next? So now inside the loop, what is next? Kappa is, well, very good. But now kappa is a condition of Hilbert n. But then what is n? N equal 1 before the loop. Yes, very good. So n equal 1 before the loop. Yes. And then now you need to print out. You need to print out the n and then the condition number, right? And kappa. So how do you print out n and kappa? So how do you print out n and kappa inside the loop? Yes, very good. So you print out, you use fprintf. Yeah. So fprintf give you the format. Okay. So fprintf, the D stand for the decimal. So you print out n, and kappa, is you can print out in a scientific format. Okay, and 1 digit before the dot and 2 digits after the dot, and then exponent form. Okay, but is it okay? What happens if you run this? What happens if you run this program? So there's one more command. Yeah, n is constantly 1. So what do you do? How do you fix that? Yes, so you just need to increase n after this. N equal n plus 1. Okay, and I think that's it. And you let it run. Okay, and you let it run. And let's say that, okay, I have to label this as Hilbert condition. Yeah, okay. So then print out the table. So do not worry about the precise value of the last entries, because different machine, you might have a slightly different routing errors for very big number. Okay, so like different machine, you can have like 1.62 like on my machine now, but I could have 1.70 on different machines, so it's not very important, but you get the idea, right? So that is question number 1. So a lot of people got this done on MATLAB Grader already. Okay, and then you can do question number 2. So question number 2, factors time. So any question about number 1? Any question about this script? Any question? So I guess everyone happy, right? Yeah. And now for question number 2, factor times. So now prompt the user for the positive integers. So how do you prompt? So what commands do you use? So how do you prompt the user for the positive integers? Input, yes. So n is just equal input. Okay, and then you just say give a value with an integers n, right? Just value n equal something. Okay, that you get n. And then construct a n by n positive definite matrix of the form A equal alpha I plus B transpose B. So alpha could be any number. Okay, I remember on MATLAB Grader I put alpha to be 0.5. But you can put alpha to be any number. So now what is the command? So what command should I put in here? So this is the question, yeah. So what command should I put in here? Well, I just assume that alpha equals 0.5, okay? To make it precise. But then how do I define the matrix A? Give me the command, I just type it in. I assume that you've done it already. Yes, so A equal alpha identity. Yes, so the command is correct. Yes, so A can be given like alpha, so we use alpha. Yes, so we forgot to define the matrix B, yeah? So the matrix B to be a random matrix of size n. Okay, and so this matrix, okay, is positively definite. So we will study it. I mean, this is just the theorem from linear algebra. Okay, so the matrix B transpose B is positively definite, and if you make the diagonal is bigger, then it will be symmetric positively definite. Okay, so now print out the CPU time taken by LU and Cholesky factorization. So print out the CPU time taken by LU and Cholesky factorization to factorize A. So how do you do that? So what command should you use? So now how do you compute the time taken by LU factorization? So we did this in the, yes, you use tick and talk, yes, but then in the middle. So what is tick and talk is before, well, in the previous lab we use CPU time, okay, but another command is tick and talk as well, but then tick and talk is like the beginning and the end. Yes, so you need somewhere in the middle. You have to write LUP equal LU of A. Okay, so this one is the time taken for the LU factorization. And you see, do not forget the matrix P here. Okay, somebody forgot the matrix P here, and the matrix L and U will not be correct. I mean, some people got complained by MATLAB Grader because if you put in only L and U, then MATLAB Grader will check and see that your L and your U will be different from the output from the LUP. Okay. So now you do the same for Cholesky factorization. So this one is LU factorization, yeah. But how about Cholesky factorization? So what is the command? Yeah, so tick and talk with Cholesky, yeah. So now for Cholesky, you don't have to give three strictly speaking, I think you can give output P as well, but you can give R is an output like this, and if you run it, you know, so this one we label it as factor times, yeah. Okay, so now you put in say 100. You see, so Cholesky is about half the time, you know, of LU factorization, right? So Cholesky, if you remember the theory, Cholesky is about n cubed over 3, yeah. So this one is about O n cubed, maybe about n cubed over 3 flops, okay. And the LU factorization is about 2n cubed over 3 flops, okay. So you see the LU factorization is always about twice the time taken by the Cholesky factorization. So this is come from the theory, and it's verified from the running the program as well. You know, you can run like for a few cases, and you can see that, you know, Cholesky is always about 1/2. I mean, it's not exactly 1/2, but roughly, okay, because there's a lot of rounding off. Okay, so that is question 1, question 2, and you can put it into MATLAB Grader. Okay, and now question number 3. So this one is an actual problem come from mechanical engineering. Okay, so you know they are building a structure like this, and you can write down the equation, you know, static equilibrium equation and on the joints. Okay, so A, B, C, D, E, F, G. So A, B, C, D, E, F, G. Yeah, so you balance the force and you just use a second Newton law. Yeah, and essentially you write down a system of 11 equations like this. Yeah, and now we can help the engineers, yeah, to solve this linear system. Well, I mean, first, you know, it's the job of the engineer to write down the equation correctly, but now it's your job to help the engineer to solve the linear system. Okay, and now you just put in this 11 equation into a matrix, right? And now, so what is the matrix? How does it look like? So now if I write down the matrix, okay, so well, maybe let me write down the system again and in a bigger form, and you can see it clearly. Oh, sorry, where's my camera? So I have to go back. So now you look at this question a little bit. Yeah, let me set up my document camera. So now okay, so now 1 second, let me set it up. Okay, so now you look at the question, yeah? And now we going to write down the equation on paper before I write out the matrix, because it looked easier to write down on a piece of paper, because you see now you have 11 equations, yeah? And the first equation is and you have 11 unknowns, yeah? So my first equation is I will write out like this. So maybe I label this one will be like so the matrix A will be 11 by 11, right? So maybe this is a column 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So maybe before I write out the matrix, so let me write out the system again. Okay. So right now I will write out. I mean, if you look at the system on the problem set, and now I just rewrite it. So I write alpha F1. Okay. So the first equation minus alpha F3. So minus alpha F3. Okay. Then minus F4 and equals 0. Okay. Yeah. And then the next one will be F2. So the next one will be F2. So this is the next equation, F2, right? Plus alpha F3. So plus alpha F3. And then minus alpha F5. Minus alpha F5. Okay. And minus F6. Minus F6 equals 0. Yeah. And so on. So you can see that it's a bit like tedious, but essentially that is how engineers work, right? You have to come up with a full set of equations. So constructing the whole structure is not easy. So now I continue to do this, and you can see that F4. So F4 here, and alpha F5, alpha F5 minus alpha F7. So minus alpha F7, then F4, yeah, minus alpha F7, minus F8. So minus F8, okay, equals 0. So this is the third equation. Okay, and then F6 plus alpha F7, so F6 minus, sorry, plus alpha F7 plus alpha F7 minus alpha F9 minus F10 equals 0, right? And then F8 plus alpha F9, so F8 plus alpha F9 minus alpha F11 minus alpha F11 equals 0, yeah? And then you have alpha F1 wow, so actually we can write down the other equation. I mean, F1 of, so we can write out the other equation in the middle, right? Because now you have alpha F1 plus alpha F3. So alpha F1 is here, right? Plus alpha F3, right? Equals 0. Okay. And then alpha, but you see the process, right? And now I want to convert this one into the system, into the linear system, the matrix A. Well, so maybe we have to write out a few more equations, yeah, because we have to write out 11 of them. So alpha F1, so alpha F3, alpha F5, so alpha F3, alpha F3, and alpha F5, yeah, equals 0. And then so maybe it's a bit crowded, but you see the process. But now let me make maybe make another. Sorry about the dense notation, but maybe let me write down again. Okay, so alpha F1 minus alpha F3 minus F4 equals 0, right? And then alpha F1, so alpha F1 plus alpha F3 equals 0, yeah? And then F2 plus alpha F3, so F2 plus alpha F3 minus alpha F5 minus alpha F5 minus F6 equals 0, right? And then you got alpha F3, so alpha F3 plus alpha F5 plus alpha F5 equal L. Okay, so this one is not equal 0, but equal L, right? And then F4 plus alpha F5. So F4 plus alpha F5 minus alpha F7 minus alpha F7 minus F8 equals 0, right? And you got alpha F5 plus alpha F7 equals 0, right? And then F6 plus alpha, so F6 plus alpha F7 minus alpha F9 minus F10 equals 0, right? And alpha F7 plus alpha F9 equal to L. Okay, so be careful here. So this one is not 0 anymore. Sorry, I have to move up a piece of paper. Now you can see it, right? But you get the idea, right? So I just rearrange the equation. And now, so 3 more equations and we are done. So F8 plus alpha F9 minus alpha F11 equals 0. And then alpha F9 plus alpha F11 equals 0. And then F10 plus alpha F11 equals 0. So now what I want is I want to convert this one into a linear system, right? And you can see that the linear system, I mean, I will convert this one into A. I want to convert this one into a vector, I mean a matrix A times the vector. Good point. So if we are balancing the vertical and horizontal force of each point respectively, why do we keep joint A? Good question. So what is the equation at joint A? Let me have a look. Good question. So what is the equation at joint A? One. B, C, D, E, F, G. Actually, I think the joint A, I think there's a, so if it could be a typo. I think if you look at this, yeah, I think this one, the equation number 1 is for HAB, right? Yeah, and equation number 2 is for AC. Okay, and then you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so 11 equations. I think this one is not very precise because, you know, I mean the joint B, C, D, I think this is not a very precise statement. But if you look at the pictures, you have 11 edges, right? And each edge, then you have 1 equations. Yeah. So I guess this could be, yeah, you see, so this means that joint B, you have equation 1 and 3 here. Yeah. Okay. And then joint C, then you have equation 2 and 3 here already. So joint A, we don't have to consider again because the equation over the edge is more important. Yeah. Okay. So we do not skip the point A, but it has been covered. You know, equation 1 and equation 2 has been covered by joint B and joint C already. Does that make sense? Yeah. We also skip D. Well, I mean, well, but at least now I think the equation is about the edge, right? And if you count the number of edges, then you have 11 edges and you have 11 equations. I think joint G, you have so F10, you know, the F, remember the F, the forces on each on each edge is given by F1 up to F11, right? And here for all the edges, for each edges, then you got on You got all the equations, yeah. So for joint, we form 0 equal F1 plus F2 okay, so actually, you know, I mean, if we look at the, I'm not very good in mechanical engineering. Okay, but we have to look back at the assumption again. Okay, so you see that A is fixed, joint A is fixed, yeah, and joint G is fixed, yeah, and then vertical loads are applied here at C and at D. Okay, so that's why we have yeah, you think the issue. So can you explain it? So yeah, A is fixed, yeah, but G is not, yeah. Okay, so yes, okay, so you are very good in physics. So I don't know, but essentially maybe that is assumption. Okay, so I just got the equation from the mechanical engineering application. So assume that we are given, but then maybe we just believe that. Okay, so the last equation for G and that for horizontal or vertical forces of G. That is a good question. I guess because G, you know, I mean, you cannot go up and down, right? Because there is a obstacle here. So I guess maybe the last equation is for horizontal force only. Okay. So does it make sense? So I'm not very good at physics. Okay. So the right hand side are vertical forces. Yeah, but you see, in this case, you know, we have only vertical forces. We have only gravity. Yeah. So I guess on every joint you balance the X and the Y component. Yeah. And in this case, we don't have any horizontal forces. We just have vertical forces. Okay. So I assume that you've checked the physics, yeah? Except for joint G. I think on the right-hand side equation are both X and Y. I think the first equation is for X component, for X horizontal force, and the right-hand side for vertical force. Okay, so you see in joint B, then you have both vertical and horizontal, yeah? Well, actually, horizontal equals 0, yeah, but in joint C, then it pull it down L, so then you have L like this. Okay, so I assume that the physics is correct. Okay, so now we just write out the equation, and now if you write out the equation, then the matrix A should has the form, you know, I mean, you can form a matrix A, and so I assume that we can write the matrix A, and now go back to the well, you see, the real application is a bit tedious, but at least we show that, you know, the solving the linear system does arise in practice, and this is a one example. Yeah. And now if I go back to the screen, so I mean, assume that you have checked the physics. Yeah. And then you can write down the equation. You can write down the matrix. So the matrix A will be so now you can write down the matrix A, yeah. So it will be 11 by 11. So the matrix A will be a big matrix like this. So 11 by 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. And the first equation, I mean, if you look at back again, the first equation is just alpha F1. Okay. So you see the matrix, you have to multiply with a vector F1 up to F11, F1, F2 up to F11. Yeah. And the matrix is alpha F1, then minus alpha here, and then 1 minus 1 here. And then the rest is just equal 0. Okay. And then you can write out a second equation. So second equation is alpha here, and then 0 here, then alpha here, and then 0, 0. So essentially you can fill up the matrix. Okay. I mean, it's a bit tedious, but that is what the real application is. Yeah. And then it's a sparse matrix because you see that there's a lot of zeros. You see there's a lot of zeros in the linear system. Okay. And then you can use, so now you can use MATLAB to solve this linear system. Okay, because and in practice you can see that the real structure could have more than 11 vertices, right? It could have like million, and then you have a million by a million matrix. But then, you know, I mean, the matrix will be sparse because one vertex is connected with only about 2 or 3 other vertices, right? So therefore the matrix is very sparse. So as it happens in practice as well. Yeah. So now I'm going to MATLAB and I'm going to set up this matrix. So now I'm going to set up the matrix, okay, in MATLAB. And you can see that so if you put in the okay, so now my matrix will be so this is my matrix. So what does it mean here? So maybe this one save it first. I save question number 3, 4. So you see, remember your matrix is a sparse matrix. So you don't want to enter, you know, like 11 by 11 matrix, right? But you can enter the sparse matrix by given the values and the index of the non-zero entries. Okay. And so this is the index. I mean, sorry, not the index, but the position. The position of the position of the non-zero entries. Okay, so alpha is square root 2 over 2, come from the equation. And then, you know, at the entries 1, 1, then it's equal alpha. the entries 1, 3 equal minus alpha, and 1, 4. So this is a row, right? So this is a row and this is a column. So you see the first row, you have only 3 non-zero entries. Okay. And then so on. The second row, you have only 2 non-zero entries. And so on. So this one you can read off from the equations. So remember, you can read off from the equation those entries. Yeah. So those indices. So this is a row index and this is a column index. Okay. And then the sparse matrix, the sparse command. Yeah. You just put in 3 vectors. So the first vector is the row indices, and the second one is the column indices, and the third one is the non-zero values. And then 11 by 11 matrix. Yeah. So this command will give you a matrix A. And now if you look at the matrix A, well, you don't see the full matrix. Okay. But it gives you exactly what you want here. So at 1, 1, at 2, 1, at 3, 2. Okay. And you can, you can manipulate the matrix, but any operation just using like the usual command. Okay. So you can define the sparse matrix like this. And now you can define the right hand side. So the right hand side, now we can assume that L is just equal 1. Let me put in. Where does the value of alpha come from? I think it comes from. Very good question. Let me go back to the. I think the value of alpha just come from the question. Yes, the angle of the semi-vertical beams. So if you go back to the. Yeah, so alpha, it's just cosine of 5/4. Are we supposed to know how to calculate that? No. This one it just come from linear. No, sorry, not from linear algebra, from mechanical engineering. So we are not supposed to know mechanical engineering. So this question is just a practical question to show you that linear system does arise in practice. Okay, so this question is not about the syllabus. Okay, so this question, I mean the part about the linear system come from the syllabus. Yeah, sparse matrix come from the syllabus. Okay, but the physics, I'm not supposed you to know that, right? Some of you might remember from your physics from mechanical engineering materials, but I'm not supposed you to know that. You see, that's why I just gave you this on those equations. The equilibrium equation are given. So what you have to do is just construct the matrix. Yeah. So given the system of linear equations, then your job, okay, is to construct a matrix and a sparse matrix, okay, and solve the linear system. Okay, and solve the linear system now is even very simple, right? I mean, you just have A backslash B and that's it. Yeah. And I mean, this is another equation. I mean, another question come from interpret the solution. Okay, but again, the whole point of this question is just for you to realize that linear system does arise in practice. I mean, what you're doing just a part of the whole pictures. Yeah. Does it make sense? Okay, so now, because I got the question like many people ask me, okay, so we studied this, but for what purpose? And this essentially this question gives you a sense of purpose of what you are doing. Okay, and now go back to the MATLAB. Yeah. So now you can give the matrix B like this, and then L will be something that you can define outside, right? You can multiply B by L. Okay, and then you just solve. So this one is what you have to do. You just solve a linear system, right? And then now you just like display what struts are under tension, you know. So it means that you just find all the positive values, yeah. So if the force are positive and then under tension, you know, you try to pull it, and if it negative, then under compression, you try to push it. Okay, so it give you the answer, right? So again, you see this one is a application of solving a linear system and give you back the interpretation on the mechanical structure. Yeah. Now you can tell the engineers that, okay, strut number 2, 3, 6, 7, 9, 8, sorry, 9 and 10 under tension, you try to stretch it, right? And the other one, 1, 4, 5, 8, 11, you try to compress it under the current assumption. Okay. And then, you know, you can try to find the maximal force. Yeah. So what strut is under the maximal force? So you define, you know, you find out what strut is under the maximal force, and you run it, and you see number 8. Yeah. So X8 is the greatest force is in strut 8. So, and you know, I mean, materials has a limit. Suppose you put more force than the limit, then it's going to fail, right? So it depends on the material. You want concrete, or you want metal, or you want different materials. Then you know, if you put a lot of force, then up to a certain threshold, then it will fail. And this one, you just find out what strut are under the most pressure or tension. Okay, because you take the absolute value. So does it make sense? So the last question is just for fun. Okay, so you don't have to worry about how to come up with equations. Okay, just give you a sense that this is an application. So any question? So maybe I just stop the recording and you can ask the question. Yeah. What does MI tell us? Okay, so MI. So remember, if you have max of say 1, 2, 3, 4, 5, yeah, then it just gives you the maximal value. But if you give like M, then I equal max 1, 2, 3, 4, 5, then it gives you two things. First, the maximal value is 5, and second thing is the index that it got the maximal value. Okay, so the I here, so that is the index of the matrix that the maximal value obtained. Okay, so because if you write say max 5, 1, 2, 3, 4 like this, then the max is still 5. Okay, but another I is 1, right? So the index that it attained the maximal value is 1. Yeah, so does it make sense? So because we want to find out what strut that has the maximal force, so that's why you need the index. Okay. Okay, so I think I will stop the recording here, and if you want to ask me anything, you can unmute. So let me stop the recording.